Yeah, the final topic in liquid chromatography is gradient separations. Okay, this is just like a temperature programming in gas chromatography. Yeah, for the rapid separation and for the better resolution, usually the oven temperature is programmed. Okay, in gas chromatography from low temperature, and you increase the temperature slowly, maybe 10 or 20 degrees C per minute, okay, until maybe 200, maybe 150 degrees C. Yeah, in that way, see, the separation uh, becomes very fast, and also, you know, the resolution is better. So likewise, but in LC, usually temperature programming is not done. Okay, rather, LC is operated at constant temperature. Sometimes the temperature may be higher than 50 degrees C, but usually a little bit lower than that. Anyway, important part in liquid chromatography is that uh, the solvent, okay, solvent, different solvents the input to the column, and uh, the ratios of each solvent is continuously changed. Okay, that's the gradient separation. By that way, if you rightly choose, uh, the right solvent and the gradient, okay, then uh, better or the separation with the better resolution and short analysis time is possible. Okay. Okay. Let's first define a dwell volume and dwell time. So we have to know the dwell volume or dwell time, because although you inject your sample, yeah, in HPLC, you know that the sample does not reaches do not reach the column right away, but since there are other volumes, yeah, before the column, like sampling volume and so on, so it takes time. It takes time for the sample to reach the inlet of the column, right? So the time, so dwell time means that let's first define the dwell volume. Yeah. Dwell volume is the volume between the point at which solvents are mixed and the beginning of the column. Okay, so you understand, right? Uh, Here we assume that several different solvents are used, so they are mixed. Okay, and at at one point. Okay, and then now the mixed solvent moves, yeah, passing through some parts, and then it reaches the beginning of the column. Okay, so that volume, yeah, means dwell volume, and dwell time is the time to for the sample to reach the column. Okay, so dwell time equals dwell volume divided by flow rate. Okay, so why does the dwell time is important? Because if you don't know the dwell time, although you program the gradient illusion, okay, then that doesn't mean that the solvent gradient mm, is not does not immediately affect does not immediately enter the column, okay, because there are there is a dual volume. Okay, first the solvent, yeah, must and solvent and your sample should pass through this dwell volume. Okay, so it's important to measure the dwell time. Okay, how do you measure dwell time? It's rather simple. You simply disconnect. Okay, disconnect the column and directly you connect uh, your the inlet tube to the outlet uh, tube. Okay, uh, and since the column is removed when you inject the solvent, and then you observe the detector response, right? And then you measure the time. That's the dwell time. Okay, here place water in reservoirs A and B of the solvent delivery system. Okay, and add zero point 0.1 volume acetone to reservoir B. So you need at least two reservoirs when you do the gradient dilution. Okay, A is for purple solution and B is for the what usually solvent. But now in this case, A and B you put water, and then but in reservoir B you add acetone, okay, 0.1% acetone, and program the gradient to go from 0 to 100% B. Okay, at first only the A, only water, and then you slowly mix. Yeah, you increase the solvent in reservoir B, and then finally you make it reaches 100%. That means that the water percentage, yeah, will slowly decrease, okay, in proportion to this acetone solution. Okay, and make it for example 20 minutes, yeah, and then you start you start the HPLC. Okay, and it will look like this one. Okay? Look at that. Now you injected at this point, yeah, time 0, yeah? And then now during this time, yeah, until this dwell time, uh, the detector response is 0 because there is no acetone. Now acetone uh, needs time to pass through, this part. Okay, and then finally the acetone now begin to uh, be detected. Okay, that's the dwell time here, yeah? And then acetone this detector response begins to increase linearly. Okay, why? Because now you increased the portion of B of acetone, right? That's the linear gradient in separation. Okay, that way you can precisely measure this dwell time. All right. Okay, but we have you have already learned the gradient illusion, with so-called segmented gradient. Okay, in a um, first part of this chapter, we already learned the segmented gradient for the better resolution, better separation. Okay, and this gradient is different from linear gradient. In segmented gradient, for example, now you have, this is the figure 12, you have 8 compounds, okay, and with only the isocratic illusion, okay, it takes a long time, maybe more than an hour. Okay, so now you started with this one, 30% acetonitrile and 70% aqueous vapor, and then here uh, um, the compound 1 2 were separated. Okay, but other compounds 3 to 8 still in the column, right? But if you keep using this 30% acetonitrile, and then these six compound may appear quite late. Okay, and then here you change, increase the percentage of acetonitrile to 45%. Yeah, here you slowly increase here, and then you stop here. Okay, and then you the maintain until how many minutes? Maybe 28 minutes, and then here 3, 4, 5. These compounds are well separated. Okay, and then so if you keep maintain maintaining this the ratio, and then compounds 7 and 8 may appear quite late. Okay, and then here again you program the acetonitrile, so increase the percentage of acetonitrile to 80%, and 20% is aqueous buffer, and then you get this 7 and 8. Okay, within maybe 37 minutes. Okay, this is called segmented gradient. Okay, this is segmented, although this part is linearly changing. Okay, but now here we are considering linear gradient. Okay, here linear gradient. Okay, and linear gradient means that the organic portion of the mixed solvent increases, okay, linearly with time, not segmented. Okay, like this one. This is linearly. Okay, here this y-axis is percentage of solvent B. Usually B means organic solvent. Okay, now until here this is the dwell time, and then from the dwell time increase. Okay, increase the portion of B till 80 something some percent. Okay, well, so this linear gradient illusion gives you better separation. Okay, and then shorter separation time. Yeah, but you have to decide first whether you go for gradient illusion or isocratic illusion. Okay, how do you do that? How do you do that? Here, this one. Let's look at this chromatogram. This chromatogram was obtained with 10% of the B, starting here at this point. Yeah? By the way, now we simply assumed that, and this dwelling time is 5 minutes. Okay, 5 minutes. Or here, I've already explained the measuring dwell time. Okay, and so here add I already mentioned that add acetone to reservoir B, and then program the gradient to go from 0 to 100% B. Okay, in the 20 minutes, for example, and begin the gradient at t 0 here. Okay, anyway, here, so this one shows that we've already measured the dwelling time is 5 minutes. Okay, now here uh, this one was done with first 10% the B. B is, I don't know, maybe acetonitrile. Okay, and then linearly increase the B percentage to 90%. Okay, here look at that. Yeah. So since we already knew that dwell time is 5 minutes. Okay, 5 minutes. So you don't have to uh, increase the B percentage from zero time, okay, because this dwell time is simply this is kind of dead time, yeah. And so at 5 minutes at this point you start with 10% B, okay, and then linearly increases, okay, up to what percentage here, 90%, okay, here 90%. This is 90%, all right, and you obtained this chromatogram, and then, yeah, to decide whether you go for gradient illusion or isochromatic illusion, you first the measure delta t. Delta t is the this one, the retention time for the last peak. In this case, is 35.5 minutes. Okay, and then the first one, this one, first peak. This is 14 minutes. Okay, so delta t is the difference between these two times, and is 21.5 minutes. Okay, this is the delta t, and then uh, take calculate delta t over tg. Tg is what? Tg is gradient time. Look at in this case here, since you change it, the solvent P percentage from 10 here 10 to 90%, okay, and then it takes how many times from here to there, yeah, this is uh, 40 times 40 minutes, yeah, okay, here this is 5 minutes, and here is the 45 minutes, okay, so this gradient time is 40 minutes. So now you calculate delta t over tg. So if that value is greater than 0.25, and then gradient illusion is the answer. But if this ratio is less than 0.25, maybe isochromatic illusion, maybe okay. Okay, but now in this case, the 21.5 divided by 40 is 0.54, which is this is much greater than 0.25. So gradient illusion is the answer. Okay, so gradient illusion is recommended. But how? Maybe this one, this gradient is best one. But yeah, let's look close at this chromatogram, right? Although the separation is good actually, right? All 8 compounds are well separated within about 35.5 minutes, okay? Then maybe okay. But look at the this in the initial part, okay? Here maybe up to maybe 13 minutes, right? This is kind of, there's nothing uh, up to about 13 minutes, right? So it is important to uh, reduce this time, okay? And then we can do much better. Okay? Now this first one is we've already seen here, okay? It was obtained with dwell time 5 minutes, okay? And this is illusion condition, okay? Change B position percentage from 10 to 90%, okay? And then let's change it, yeah, up to this point, right? Uh, for example, I'm sorry, here, hmm, the this one, peak one appears at maybe 14 minutes, okay? So here, up to 14 minutes, yeah? So we can, reduce this time quite a bit. How? By changing, by, not by starting the 10% B, but we can start with 30% B, okay? 30% B. And then this one, this peak, the positive peak appears quite earlier, right? From 14 minutes to down to maybe 5.5 minutes. Okay, so analysis time became quite short. Okay, and then uh, change the B percentage not to 90%. Why? Because here already at this time 35 minutes, right? This one, let me see, is less than 80%. Okay, so you don't have to go to up to all the way up to 90%. Okay, that's too much actually. Yeah, you understand? Maybe 80%, maybe enough. Okay, so that's why the second one was obtained by changing the solvency B percentage from 30% to 82%. Okay, and then we get this one, and then all these uh, 8 peaks appeared less than 32 minutes. Okay, so several minutes was shortened compared to uh, this chromatogram A, but still maybe you can do better. How? The, while maintaining this illusion, gradient illusion, the same, but uh, you know the uh, the gradient make the gradient more steeper. Okay, so this one was done. Uh, let me see. Although the gradient time is 20 minutes, is the same, but of changing the this p ratio rapidly. Okay, and here look at that. This one was obtained over 40 minutes. Okay, but this one was obtained with over 20 minutes. Okay, 20 minutes. Steep gradient. So gradient time is 20 minutes here in this case. Let me see. In this case, gradient time. Let me see. No, no, no. It is. I'm sorry. This is 40 minutes. Okay. Yeah, here. So by changing the gradient time, uh, we can further shorten the separation time. Here, look at that. Hmm? Do you like this one? Maybe, but there is one little problem in this. The chromatogram C, which is the compounds 6 and 7 are not well separated in this case. Yeah? With the steeper gradient, some compounds are not well separated. Yeah? But this one, in this case, this is better, right? So it's up to you. If you want this chromatogram, although the 6 and 7 are not well separated, and then you can do this one, right? But if you want all the compounds are well separated, maybe the middle one is the answer. Okay, so here is the explanation. Okay, I've already explained in detail. Okay, now this is the end of chapter 24, uh, liquid chromatography. Okay, here is the homework problems. So don't forget to upload your answers to the eCampus. I will check all at once. All right. Okay.